problem number 2, the load P is supported by two concentric steel spring arranged as shown in the figure. The inner spring consists of 30 turns of 20 mm wire on the diameter of 150 mm. The outer spring has 20 turns of 30 mm wire on a mean diameter of 200 mm. Use the modulus of rigidity equal to 83,000 megapascal. Situation A, give the load that the inner spring could carry as Situation A, give the maximum load that the inner spring could carry, so as that AC, the shearing stress of 140 megapascal. B, give the maximum load that the outer spring could carry, so as that AC, the shearing stress of 140 megapascal. And C, give the maximum load that the spring could carry. So, first is we establish first the given. So, ilista muna natin yung mga given dito sa problem natin. For the inner spring, we have 30 turns. So, N2 is equal to 30. And the wire diameter is 20. So, we have here. The wire diameter is equal to 20 mm. And the main diameter is 150 mm. So, that is equal to 150 mm. And for the outer spring, we have the number of turns is equal to 20. The wire diameter is 30. And the mean diameter is 200. And we have the modulus of rigidity equal to 83,000 megapascal. For the situation A, we are asked to compute for the load carried by the inner spring. So we use the formula maximum shear stress is equal to 16 PR over pi d cubed multiplied by 1 plus d over 4r. And since we are in inner spring, so this is R2, this is D2, this is D2 here, and this is R2 here. And we have the maximum shear stress, which is given, that is 140 megapascal. So we have here 140 megapascal is equal to 16. The load P here is unknown. So we have P2 multiplied by the radius 2. So since the diameter here is 150, so the radius is 75 over pi. This diameter here is the wire diameter, 20 mm cubed multiplied by 1 plus the wire diameter, that's 20 mm, over 4 multiplied by the main radius, half of 150 mm, that's 75 mm. And computing for the load carried by the inner spring, we have 140 is equal to 16, the unknown load, times 75 over pi times 20 cubed multiplied by 1 plus 20 over 4 times 75. And shift solve equals, and that would give us 2,748.89. So, and this is equal to 2,748.89 Newton. So if the choices is in whole number, so we could approximate that this is equal to 2,749 Newton. and this is our answer. So situation B, we are asked to compute for the load carried by the outer spring. And we have here the stress is equal to 16 P1 R1 over pi diameter 1 cube multiplied by 1 plus D1 over 4 R1. So we have here the stress for the situation B, which is also equal to 140 megapascal. So we have here 140 megapascal is equal to 16 P1. The main radius 1 is half of this 200 mm, and that is equal to 100 mm over pi multiplied by the wire diameter, that is 30 mm cube, times 1 plus the wire diameter, that is 30 mm over 4 multiplied by the main radius, which is equal to 100 mm. So computing for the value of the P1, we have 140 is equal to 16x times 100 over pi times 30 cube times 1 plus 30 over 4 times 100. Shift solve equals, and we have 6,904.20. So we have here 6,904.20 Newton. Now if we are going to approximate this to the nearest number, so we have here 904 Newton, and this is our answer. For the situation C, we are asked to give the maximum load that the spring could carry. So we have from the idea of the deformation is equal to 64 P R cubed N over G D to the fourth. So we assume that the deformation in the inner spring is equal to the deformation of the outer spring, and we could say that the deformation 1 is equal to the deformation 2. So for the deformation 1, that is the outer spring, we have here 64 P1 R1 cube N sub 1 over G D sub 1 raised to 4, that is equal to 64 P sub 2 R sub 2 cube N sub 2 over G D sub 2 raised to 4. Substituting the values here, we have 64, the P sub 1 is unknown, and we have the R1, that is for the spring 1, so we have half of 200, so that is 100 mm raised to 3 for the outer spring. Number of turns for the outer spring N1 is equal to 20 over the modulus of rigidity, that is 83,000 in this denominator here from the right side of the equation, 20 raised to 4. And that would give us 3.2. So we have here 3.2 of P2. So from the previous solution, the P1 is equal to 6904 Newton, and the P2 is equal to 2749. Now, when P sub 2 is equal to 2749 Newton, we substitute that in this equation here, and we have P1 is equal to 3.2 times 2749 Newton, and we have P1 is equal to 3.2 times 2749, that is equal to 8,796.8 Newton. So we have here 8,746.8 Newton, and this P1 here is so as you can see here, we have the allowable P1 as computed from the previous solution, which is equal to 6904 Newton. This value here is greater than 6904 Newton. Now, we say that in this situation, the outer spring fails. So since the P1 here is greater than 6,904 Newton, so we used the value P1, which is equal to 6904 Newton. And when P1 is equal to 6904 Newton, then from this equation, we have P1 is equal to 3.2 P2. Then we have here P1 is 6904, that is equal to 3.2 P sub 2. So we have P sub 2 here is equal to 6904 is equal to 3.2 X shift. So equals, and that would give us 2157.5. So we have here 2157.5 Newton, and this 2157.5 Newton here is less than the P2 computed, which is 2749 Newton. We have to take this 2157 Newton since this is safe. So in order for us to compute for the value of the load P is the sum of P1 and the P2, and that would give us 6904 Newton plus the P2, which is 2157.5 Newton, and the P here is equal to 6904 plus 2157.5. This is equal to 9061.5. So we have here 9061.5 Newton, and this is our answer.